Hello, everybody. Thanks for attending the session. Uh, I would like to start by thanking the organization because we had quite a few hiccups to get here. They had a hard work for organizing it, and suddenly we had a flooding problem. This image is from yesterday evening next to our hotel. As you can see, we had serious trouble with the flooding, and they had to go all online. So great work, showing adapt capacity clearly. And so thanks for all the organizers, to all the organizers. So today's session, we're going to talk on how by implementing asset management systems, we can reduce the risk caused by climate hazards on different types of infrastructure. This session is organized by INES, which is a Spanish engineering company, together with the collaboration of the World Bank. And the theme that we're going to be following for this session is basically this one. We're going to start by an introduction of the team and of the session. We're going to go with a description of the methodological framework that we are applying at the moment of implementing asset management systems. And afterwards, we're going to show 3 case studies that are going to address different type of infrastructure as example of how this methodological framework is applied and what can be achieved with it. And finally, we will end up with conclusions and any questions that you might be interested in asking. So just to start with, uh, I'm here next by to Enrique, and online from our office from Madrid, you will be seeing also Marta per Tierra. We are all disaster risk management specialists. And besides our civil engineering background, in the case of Marta, also she has an environmental science background. Additionally to the civil engineering, we want to highlight which is the experience that we got on this type of projects. This is the places we have worked in the past 10 years, working in issues related with risk reduction and asset management systems. As you can see, we have quite an extensive experience in the Caribbean region, but we also have experience in America, Europe, Africa, Asia, and now we're working in the first states of Micronesia in the Pacific. So another thing that I want to highlight before going ahead is that we are facing, or we are working on the preparedness of the disasters. That is, we are not dealing with disaster response, but disaster prevention. So this that we are going to be explaining, or that we are going to be presenting now, is more focused on that, on preventing and trying to prepare our infrastructure in order to better withstand the potential hazards that you might be facing. But anyhow, we also have to say that these tools can help also on the emergency response. Which are the main session keywords that we would like to highlight? Well, maintenance. This is the first one. You need to make sure, you need to keep in mind that that up to now, all organizations have been willing to build new roads, new houses, new buildings, and new railway tracks, probably. No, but now we have a great amount of assets built, and it came the time already of balancing the allocation of the budget towards maintenance instead of new construction. Another one is data, the importance of having accurate data, and not only accurate but tailored to the project needs. Additionally to that, we need to have in mind how to deal with it and how to store it. The third keyword would be versatility, which is how can, using the same methodological framework, we can address different assets. And the fourth keyword would be budget optimization. How can we, doing informed decisions, improve the budget allocation in order to get the risk reduction that we are all willing to achieve. No, that would be the last keyword. Here, I want to just introduce which are the main challenges our clients are facing, which is high exposure. We have limited resources for addressing the problems. We tend to have a reactive approach in maintenance. We have a lack of data, and there are no decision support tools implemented, or the ones that are implemented might be a bit complicated to maintain and keep up. In order to expose this, we would like to use these 3 case studies in order to show you how applying this methodology we can achieve great progress and get the target of this key goal and keywords that we were mentioning. No, that we presenting a project in Anguilla for managing 155 public buildings, 2,000 kilometers of railway line in Spain, and 360 kilometers of public roads in the further states of Micronesia. Here's just to show you, this would be the case of the problems faced by the people of Anguilla. This is in the case of the railway tracks in Spain, and this would be the case of Micronesia. So once completed the theme and the session introduction, I'm going to go ahead with the definition of the methodological framework that we are applying. And just go ahead. Just start by mentioning that the global framework is based on the ISO 55000 as the global framework is based on this. And additionally to that, we also use additional guidelines, and that can be national or international ones, and that help us define on one hand indicators, and on the other hand how to develop specific asset maps that are needed for having a good implementation of an asset management system. I would like to start introducing what asset management is. And for that, we have chosen here the 2 definitions that the ISO standards contemplates. One is activity that translates the organization objectives into asset-related decisions, plans, and activities using a risk-based approach. This is basically translating that you have a set of assets that you're willing to have in a level of with a certain level of service to offer to your users, and for achieving that you need to doing certain interventions on them, because if you don't do anything within time, they're going to get deteriorated, and if you have a certain natural hazard event, you might have the problem of having serious damage on them. So you need to define your objectives and take decisions and plans in order to be able to achieve that level of service is reached as much as possible, taking in consideration not only the condition but the climate hazard. Secondly, we have asset management supports the realization of value while balancing financial, environmental, and social costs, risk, quality of service, and performance related to assets. Well, what we want to highlight here that the prioritization of activities is not only carried out based on monetary cost, no, that you need to make a balance between economic, environmental, and social costs. And you need to, obviously you don't have the amount of money to address all the problems that you're going to have, no, but you need to get to an optimized solution in which, with the money you got, you get the best performance for your set of assets. So, which are the main objectives? Increasing resilience, improving or optimizing investment, and increasing the capabilities of the managers by implementing this asset management system. So at the end, I say, one of the keywords is maintenance. So we are working towards a resilient asset management, which implies passing from a reactive approach in which the expenditure is actually done just after a failure, towards a preventive approach where we already incorporate the required. And finally, we have the risk-based approach, which doesn't only include the condition, but also it takes in consideration the climate exposure. And how do we do this? Well, we do it using key performance indicators. No? At the end, we were saying that we are looking for a risk-based assessment. No, that risk-based assessment translates in a key performance indicator, which is what we call the risk of failure. No, that at the end is what marks the decisions that we're going to be doing. This risk of failure is defined by international standards as the probability of failure times the consequences of that failure. The probability of failure is what we call vulnerability of the assets, and the consequences of failure is what we tend to call criticality. In the case of the vulnerability, that one is marked by these two aspects. No, on one hand, the asset exposure, which indicates how your assets are exposed to the hazards that can be subject the country to. As example, for example, here we had in Florianópolis, we had flooding problems, but probably in Sao Paulo they didn't. So here the exposure is higher than in the case of Sao Paulo. And afterwards, we have the asset sensitivity, no, which is how the asset can be sensible to uh, the external action of climate exposure, which is defined on first hand by the condition. Obviously, if you have something in bad condition, it's gonna withstand worse than if it's in great condition. And afterwards, we have the coping capacity, which basically is how well is the design of the asset for withstanding the climate exposure. In terms of the asset criticality, what does this define? We could maybe summarize it as the importance that the asset has got within the network, and it's based on economical, social, and environmental indicators, as we were mentioning before. So once this said, I pass the stage to my colleague Enrique, who is going to present you the case study of Anguilla that is focused on the buildings. So Enrique.
Okay, well, first of all, um, hi for everyone, and now I'm going to start with the case study of the buildings in Anguilla. Okay, well, the name of this project is the Technical Assistance Developing Assets Management Capacity for Buildings Operated by the Government of Anguilla. Well, first of all, I want to explain something about the location of the island and also something about the general introduction. Well, the island is in the East Caribbean. Okay, it's a small island with only 102 square kilometers extension, and there are living more or less around 15,000 people. Well, the first objective of this project is try to um, create a tool that helps to the government of Anguilla to manage the maintenance of different buildings, and also this tool enables to predict more or less what's um, the behavior of the buildings against the heavy rain or against the hurricane. Well, first I'm going to start with the preventing maintenance management. Okay, that is the like the second level of maintenance that we explained before. Well, so first of all, it's necessary to have all the information in a database. Okay, then when we have all the information of the different buildings in this database, it's possible to develop a physical condition assessment. Okay, when when we talk about physical condition, we are talking about the conservation state of the buildings. Okay, and then comparing this physical condition with the ordinary level of service, the level of service is the level at which the client of the building want to have the buildings. Okay, so comparing these, it's possible to estimate the maintenance and repair costs. Okay, then using different indicators like the facility condition index or the asset priority index, it's possible to make a prioritization of the maintenance and repair activities. Okay. Well, next, I'm going to start with the third level of maintenance, that is the risk-based maintenance management. Again, it's necessary to have all the information, okay, in collecting in a database. Well, then with this information, it's possible to develop the physical condition assessment, okay, and also the design condition assessment. The design condition assessment refers to the coping capacity of the buildings. It's the how these buildings behaves against a hazard. In this case, it's here again, okay? And with the physical condition assessment, uh, we can achieve the maintenance and repair cost, and the design condition assessment gives the retrofit cost, okay? Then combining this physical condition assessment and the design condition assessment is possible to calculate what is the vulnerability of the building. It's important to say that in this case, the island is quite small. So there are no difference in the exposure, okay? So that's why we don't introduce the exposure um, in this project, okay? And then again, um, if we compare the vulnerability with the hazard level of service, we can estimate the combined cost. Okay, the combined cost is the combination of the maintenance and repair cost and also the retrofit cost. And again, with the different indicators, it's possible to make a prioritization of the maintenance and repair activities and also the retrofit activities. Well, in the database, we collect different kind of information. We have information about general data like the name of the building, the typology of the buildings. Also, we have geographical and geometrical data like GPS information. Also, we have engineering and structural data. Also, we have engineering facility data, including surface data, and the budgeting data, and of course, the key performance indicators that help us to prioritize the activities of maintenance. Well, here we have some example of the questionnaire that we create with the Kobo Collect app. That it's an open source app. Okay, that um, okay, and then when we have these questionnaires created, um, we go and we do the different inspections, okay, in the field, in the different buildings, and we fulfill all the fields of the questionnaire, okay? And here we have some examples of what are the fields of of this questionnaire. We have here, for example, information about the general data. Also, we have information about geographical data, information about the different elements of the buildings. And another thing it's quite important is that we can also collect all the information about the damages of the different buildings. Okay, and we can include the severity of the damages, extension, and also we can take picture of that damages. Well, in here we have some photos, okay, of the inspection of our team, Ines team, okay, doing some material tests, okay. Well, now I'm going to explain a little bit about the physical condition methodology. This methodology follows um, the researches of FIME and also the research of the American Society of Civil Engineering. Well, once we know we identify the damage, okay, it's necessary to select what's the building subassembly, okay? So for example, in this case, we are talking about the roof structure. Then it's necessary to select the elements, okay? In this case, it's joist. Then we select the material, okay? In this case, steel. Then it's necessary to select the damage, okay? So in this case, we're talking about corrosion. Then we select the intensity of that damage, and also we select the extension of that damage. So with all of these, we can calculate, we can estimate a score of the physical condition. We can calculate the score of the conservation state of the building. Well, how we calculate or how we estimate the design condition? Well, again, we use the FEMA information. In this case, we use the benefit cost analysis tool. Okay, this tool um, estimate the damage curves of the different buildings based on the characteristics of these buildings. Okay, so with these curves, okay, it's possible to know uh, what is the wind speed that the building can withstand with less than a 5% of damages. We say that if the building withstand um, with less than 5%, we can ensure that this building is going to withstand the wind speed. Okay, that's why we select 5%. So, for example, in this case, uh, in this example, we have a damage curve, okay, and with less than 5%, it's a wind speed of 125 miles per hour, okay? That is why how we can calculate the wind speed. Okay, then using the Saffir-Simpson scale that compare the wind speed and also the hurricane category, we can estimate more or less the hurricane category that this building can withstand. In this case, if we have a wind speed of 125, it's hurricane category 3. Okay, so with this hurricane category, we calculate the design condition. Okay, in this case, the design condition is 3. Okay, well, and now how we estimate the vulnerability. Well, how we combine the physical condition and the design condition to estimate the vulnerability. Well, with the physical condition, we you obtain a score between 0 and 100 of the conservation state, okay, of the building. And with the design condition, we obtain the wind speed, okay, that the building can withstand. Okay, so using this formula, the wind speed multiplied by the score of the physical condition divided by 100, we calculate a reduced wind speed. Okay, again, with the Saffir-Simpson scale, it's possible to know um, what is the hurricane category that correspond with this reduced wind speed. Okay, and with this hurricane category, new hurricane category, we can estimate the wind vulnerability. The wind vulnerability. Well, now I'm going to explain a little bit about how we estimate the costs. Okay, and I think that it's more friendly if we well, if I explain the methodology with an example, okay? This is an example of building in Anguilla in the airport. It's a concrete building with concrete beams and concrete columns, okay? And here we have an outside photo and also an inside, okay? Well, and what is the conservation state of this building? What is the physical condition of this building? Well, here we have some photos of the different damages of these buildings. We have a lot of cracks in the columns. We have corrode reinforcement of the columns. Also, a lot of moisture in columns. Also, we have cracks in the slab, the foundation slab. Okay, also cracks in the walls, a lot of moisture, spalling in the concrete roof, and also some corrosion in the mechanical bracings. Well, so we calculate the maintenance and repair cost, assuming all the maintenance and repair costs of each subassemblies. Okay, so the sum of these subassemblies enables to calculate the total maintenance and repair cost. Okay, so first of all, I want to start with the first value of the formula. It's alpha. Okay, and these values are related directly with the physical condition. Okay, more or less, this value refers to the percentage of damages of the subassemblies. Okay, so an alpha of 0.58 means that the damages of this subassembly is more or less 58%. Okay. Okay. Then we have another value that is called the cost ratio. Okay. The cost ratio is the proportion of the cost of the subassembly compared to the total cost of the building. Okay. So in this case, these are the subassemblies that have some damages. So we should select, okay, the cost ratio of these subassemblies. Also, we have this value that it's extension factor, and these are related also with the physical condition, concurrently with the extension of the damage. Okay, so if we have low extension, okay, this factor reduce the cost of this subassembly. And finally, we have the building value. Okay, the building value is calculated multiplying the building replacement value per square feet, multiplying by the total area of the building. This building replacement value is based on the occupancy class of the different buildings. Okay. Um, and in this case, it's government and general services. Okay, it's important to say that the building replacement value and also the cost ratio needs to adapt to the different project. Okay, so it's not constant. Well, so first we calculate the building value. Okay, the building replacement value multiplying by the total area. Then with the formula, we can calculate the different cost of the different subassemblies. Okay, and finally we sum all these costs and we have the total maintenance and repair cost. In this case, is 70, more or less 76,000 of dollar. Okay. Okay. Now I'm going to explain about the retrofit cost methodology. Okay, and first of all, it's necessary to to explain what are the measures, what are the retrofit measures that we are going to implement. Okay, these retrofit measures depends on the typology of the buildings. For example, in concrete buildings with concrete roof slab, okay, uh, we can put shutters in case they are missing, okay, to protect the windows and also to protect the doors. Well, in case of masonry, the masonry buildings with wood roofs, also we can put shutters, and also we can improve the anchorage, the wall roof anchorage. Okay, for example, if we have two nails or we have a screw, we can improve these anchor using straps. And finally, we have the buildings that are also masonry, but in this case, they have metal roof and also um, the steel buildings with all the structure is steel structure, okay, including the roof. So in this case, again, we have the shutters. We have also, in this case, we can improve the metal deck attachment, and also we can change the whole metal sheet. Okay, these are the retrofit measures. So now this is another example to explain how we calculate the retrofit cost. And well, this is an example of a metal building. It's a salt water plant. Okay, and again, using the using the benefit cost analysis tool of FEMA, okay, we can know what's the current situation. And when we talk about current situation, we talk about how these buildings behaves against a wind in this moment. Okay, without the implementation of the retrofit measure. And the max improvement is what happens if we implement these retrofit measures. Okay, so in this case, in the current situation, okay, we have well, the wine exposure is exactly the same. Okay, it's open cost. The shutter is not applied because there are not shutters in this building, but we have the roof deck edge in. Now it's an all deck, okay, and the roof deck attachment it's a normal deck attachment, so it's standard. So we can, in this case, we could improve the roof deck and also the roof deck attachment, okay. So with the current situation, we obtain a wind speed of 110 miles per hour, and if we implement this retrofit measure, we can achieve a, um, a wind speed of 155 miles per hour. Well, then using this formula, the first factor is the relation between the cost of the measure compared the with the cost of replace the subassembly. And this is the cost ratio. The cost ratio is exactly the same that I explained before. And finally, we have also the building value. Okay. So in this case, if we change the metal leg, okay, we are changing the whole element. That's why this value is 1. Okay. Then we have the cost ratio and finally the building value. Okay. So the total retrofit cost in this case is close to $25,000. Well, then once we have all the information in the database, now it's important to know how we are going to show this information, okay, to the client, because this is so important. You have all the information, but also you need to show this information in a proper way, okay. So to do this, we use the Power BI software that enables to create dynamic graphs. Okay. For example, in this case, we have a static photo of the physical condition of the buildings of Anguilla. Here we have a pie chart with the physical condition of the different buildings, and more or less the 80% of the buildings are in good condition in 4 on 5. And for example, we can select those buildings with low physical condition. Okay. we select here. Okay, we select only these three buildings, and also we can select, okay, the asset priority index means the importance of the building, or the relevance of the buildings for the country. Okay, so if we select, for example, an asset priority index of 100, okay, yeah, we can see here in the map the location of this building. Okay. Well, in case of the vulnerability, we have exactly the same static photo. Okay, so this is the results of the vulnerability. Okay, the vulnerability in the current situation. Okay, so again, we can select, for example, those buildings with low vulnerability, and also we can select those buildings with an asset priority of 100. Okay, and again we have here the location of that buildings. Okay, and if I put the mouse close to the building, to the point, we can know what's the name of this building. Okay, and also the cost, and also what are the GPS coordinates. Well, and now this helps also to prioritize the different activities of maintenance. Okay, so here we have the pie chart also with the buildings that need maintenance, the buildings that don't need maintenance, and also we have here uh, a group of buildings that have um, that the cost or the facility condition index, that means the relation between the cost of fix that building and the cost of replace is very high. Okay, so if this indicator is high, this means that it's better to replace the building than fix it. Okay, so if we select those buildings that need uh, preventive maintenance, okay, we have here also the asset priority index. Okay, and we select the asset priority in the building with an asset priority index of 100. Okay, and now, for example, we can select those buildings with lower condition. Okay, for example, we are going to select the physical condition of 2 and also of 3. Okay, so now we have a list with all the buildings that need to repair first. Okay, and also here we have the total cost of that intervention. Okay, and in this case also we have exactly the same, but now we are talking about the risk-based maintenance. Okay, so again we can do exactly the same. We can select the buildings with the that need maintenance. Then we can select the buildings with asset priority index of 100, and then those buildings with lower vulnerability. Okay, and again, okay, we have the results and in this list, and we have the sum of all the intervention that the cost of the all intervention in these buildings. Okay, well, okay, okay, now I I want to do a questionnaire with you. Okay, so you can scan this code, and you can solve this questionnaire. Okay, I think that you can do it in a couple of minutes.
Yeah, anybody's answering. I think we have 6 people connected, but you can
Yep.
wait. So wait, we can stop sharing maybe. No? Go back to. And here we can see on the forms.
Maybe they need yeah.
Sí, no, you have we give 5 more minutes, 2 more minutes.
Yeah, we give 2 more minutes.
You can.
Yeah. Okay, so now, okay,
Two.
okay. So the first question, on what do preventive maintenance activities depend? In this case, the answer correct is the physical condition. Okay, and how the design condition is calculated using the damages curve generated by FEMF, and why the exposure is not taken into account when calculating vulnerability, because no difference in exposure due to the small size of the island. And finally, what is included in the combined cost, the maintenance and replacement cost, and also the retrofit cost. Okay, so now is we are going to talk about the case study 2. So I've give the control to David.
Well, hello everybody. Thank you for continuing there. Those that keep connected, and please do not hesitate to pose questions if you have any during the session. If not, we can solve them at the end. Yeah, I'm going to address the second case study, which is developed in Spain, and well, it addresses the railways flooding risk under a return period of 100 years scenario. Okay, so well, I believe that you know where Spain is, part of Europe, and here I'm presenting a bit the project scope. The first thing that we can say is that the objective was to identify the sections to study further in detail, because our railway administration is aware that they have a high or extensive railway network, and they cannot achieve doing all the activities of retrofitting and resilience improvement. So they need to reduce and prioritize. No, so that was the main purpose, to find which are the the most vulnerable sections to address. No, and for that we had to analyze the 2,000 kilometers of railway land that we have in our country, and against against flooding, as I say, no, pluvial, fluvial, and maritime flooding. Uh, well, it's worth mentioning that when you analyze flooding issues, you need to consider watersheds, as you might be aware, no? And watersheds are not just around your asset, in this case the railway network, but uh, influence a much bigger area, no? In this case, what I want to highlight is that we had to address almost 500,000 of square kilometers of watershed area, no? Which is huge, and it implied a challenge to be completed in 15 months. As a result, we could detect which are those most vulnerable sections, and as the client was happy, we got an extension of 9 months in order to continue taking advantage of the results that we achieve, and seeing the way of how can we start another system for them to additionally to the detailed studies that are going to be performed of different sections, how can they use the information that we provided in order to implement an alert that tells them in advance, a bit in advance, when the problems are gonna be happening. So in this case, the project approach is a bit different than the previous one of Enrique. In this case, the condition didn't interest our administration. Is not that it didn't interest as part of this project, but because it's being analyzed also by our firm uh, in another project based on advanced analytics and machine learning. So here in our project, we are just calculating the vulnerability as the exposition to the hazard. If we go back to the original sketch that I had presented before, basically here we are just reducing our analysis to the asset exposure, okay, in order to obtain the vulnerability. So which are the main principles or the main uh, advances that we are including in this study? No? Well, it's worth mentioning that we are using an open source program. It's thanks to the American, how do you say, U.S. Army, that is called ECRAS, and that in the new versions allow doing 2D hydraulic modeling and allow having an approach based on rain grid modeling. Why is this interesting? Well, it's interesting because first of all, you have two dimensions. Well, two dimensions in surface, I mean, and it provides also depth, obviously. And why is this very significant? Because previously, the analysis were done mainly 1D, and that implied that mainly you could only model the rivers, and now you can get all the watershed involved, and then you cannot necessarily only include the flooding, but also sorry the fluvial flooding, but also the pluvial flooding, which is the impact of the rain that doesn't fall on the river side. So uh, for doing this, what we need to do in this case, what we needed to do is to make a proper rain characterization. Okay, and that is an important issue and is an important aspect related with this approach, which because you have your asset depends where it's located, depends the exposure is going to be different, and as you may understand, you can experience very different types of rains within a different area. No, you can have longer but maybe more homogenic rains. You can have shorter but more peak and intense rains, and the duration can vary and the intensity can vary. No, so what we did is first of all define which are the critical rains that are going to be affecting our railway network, And for that, what we did is cut the railway network with our rivers and define the concentration times and search, in the case of smaller watersheds, peak intensity diagram for defining the precipitation. And in the case of the bigger sheds, we were going more to an homogeneous due to the area that is covered, homogeneous distribution of the rain. Here, what I'm showing in this part of the screen is that we were using different gauge stations gauge stations for the precipitation. And what we do is, we collect the information from the rain and historic for the past 30 years, and by well statistics, we obtain the rain today. And based on the Thyssen polygon distribution, we assign an area rain distribution for each of the watersheds. Well, here you can see an example. Here in black, you have on the top the railway line that goes over here. In blue, you have the river network. That in green that it was appearing there are the different intersections of the railway line with the river that defines the concentration times. And obviously, we are basing everything on digital elevation models, and we use together with that infiltration and roughness information layers to run a simulation that represents a physical base model of how the flooding occurs in a region. What is worth highlighting in this case that as you will see, it's not a static model, no, it's a time based. So we're going to be able, besides of taking out results of different sections at different points, we can see how the inundation is going to take place in time. By this, I mean that you have here when do you get the peak flow, no, for your section, and how long it takes from when it starts raining until you get that. Additionally to this I have this other example in which you can see here how the progress of the inundation goes, and in this case we are using a different map layer to support the representation. In this case, the physical map that probably it gives you more information than the digital elevation model that was showing before. No, and this tool also allows you comparing and with other informations, no, that can be implemented as different layers, and this is very useful because it allows you to calibrate the model at the end. So once we had the flooding, because now we have the flooding, we have the program, we run the simulations, we have all the flooding areas, but how do we classify this, and we categorize the vulnerability of our railway network? Well, we used how do you call it, a traffic light system, based in red, orange, and green. And this responds a bit to a maintenance strategy. If the level of the water overpasses the embankment, you're going to be having the ballast in the track affected by the water, and then the maintenance interventions that you're going to have to carry out are going to have to be done from the top of the platform. So that means that your railroad network is not only going to be affected during the flooding, but until the repair is undertaken. So this is the worst case scenario. Afterwards, we have in orange when the level reaches it affects the embankment. It doesn't reach all the way to the top, but it's affecting and has certain local failures that the good thing is that they can be addressed from one of the sides of the platform, not needing to interrupt the traffic, and maybe just introducing speed reduction, no, or limitation. Sorry. And finally, we have beneath that you don't have any major intervention to be done, and then the traffic can go without any interruption during all the process. So once we do that, we need to present it to the client. And for doing that is where we implement an asset management system. In this case, that management system, instead of being based on an Excel sheet and afterwards using tools such as Power BI for prioritizing, we used in this case a web-based system. And well, I'm showing here a picture of it, but you can, if you want, you can go into the QR code, and you have their name and password to, well, if you want to test a bit what the client can see. I'm sorry that it's in Spanish. We have other tools in English, but this one is for the Spanish administration, so we have it in Spanish. However, what we are showing here is the flooding maps, and over the flooding maps, we are representing, as you see, the railway network in different colors. No? And here they can see visually which are those sections which are more vulnerable to flooding, and also track where the flooding is coming from. Additionally, these layers have got, as any GIS system, they have obviously information associated that you can display, such as the railway line name, code, kilometer points in which these events are happening, and things like that. Okay. Uh, Once this has been said, I want to well present more about the challenges that we encountered or the lessons learned, during this project, just in case you have similar experiences. First of all, as you can imagine, we had a big extension to analyze, and each area had to require many different activities or many different tasks to be undertaken in order to achieve the final result. So at the end, we had to automatize and program certain things, because that if not, we couldn't match the the time frame that we were expected to fulfill. Second thing that I want to highlight is the volume of information. This software and this simulations are great, but have this disadvantage of generating very huge files that are not easy to handle and to manage, and you need a special system in where to store them. No, because at the end, for example, in our case, we were storing them in our local server at the office, and everybody at the office was complaining because it was lowering the performance of all the speed of the server for other people working in other projects. So what we decided is, well, let's go on the cloud. That this is you can hire and increment your space very easily, and you avoid this type of problem. Additionally, obviously, we have a local hard disk in which we store all the information, but the cloud is what we recommend for working on this. Finally, well, or thirdly, sorry, we have computational time. Okay, once again, these simulations are great. The only thing is that there are many simulations to be run. Think that you need to define many types of rain per watershed. As we were saying, we have as many rains as concentration times, as little green dots that were represented there. So we need to simulate many different cases, and each case is it takes its time. So at the end, you need to use either many computers that take occupy all the office and they cannot work in anything else, or additionally, as we did here, use cloud services, no, in order to be able to run many simulations at the same time and not collapsing an office. And finally, one thing that I want to highlight that is also from our perspective, an achievement of this project is how to represent on a web-based system uh, layers of information that are so heavy, okay? Because it's an issue, no? How can you uh, make visualize these layers independently of your internet connection, or at least that is not so dependent on it. No, and for such purpose, we came out with the development of a local WMS server in which we were storing this, and we connect the platform to that one. And this way, well, we can allow the client to access and visualize these layers of information without suffering the problems of well, having their own server, or the server that they use filled up with processes in order to load different layers. So as I said, that was up to the moment what we have done, and now we are working on the alert system. What I'm going to just talk about one of the alerts that we're going to implement. Uh, Not to bore you, but if you are more interested, you can obviously contact us, and we will inform you more. So we are using in Spain. We have a system of flow gauge predictions based on flow gauge registers. Okay, you can see here an example. This is one of the this is well, the longest river in Spain, which is Rio Ebro, and in this case, each dot is a different gauge. And as you can see here, I took this picture yesterday. So we can have a flow prediction for up to 5 days. Okay, 5 6 days. So that is quite interesting, because well, if you are able to establish a threshold limit for for the flooding, you can go further up and limit that, and then you have a 5 day prediction that can tell you when are you going to achieve that problem, if you ever achieve it, that limit, I mean, and then when are you going to get the inundation further down. So you can get 5 days or 6 days um, prediction, plus the time that the flow reaches further down. Okay? So how do we do that? Well, basically, what we do is we select a set of sections that are in red, okay, that are flooded according to the return period of 100 years, and we select one of the flow gauges that is uh, river upstream. And then what we do is we define the threshold flow by taking the section of our model and seeing which is the maximum flow that we reach at that point. Okay, and then this way we establish the threshold, and we can establish an alert based on that value of flow. With this value, additionally to that, the model would allow knowing how much time it's going to take from this point to our lower section, that is from this point to this section here, that we're analyzing the flow to reach. So we could have, as I say, 5 day prediction plus the time that the flow takes to reach down here. That would give enough time, maybe not to implement a mitigation measure, but yes, an emergency response plan. Here, I leave you with the proposed questionnaire for this case. And well, it's very, very, very simple, just 3 questions. And well, just if you are interested in and you want to answer them, we will be happy to attend you. We leave you 3 minutes, and we continue with the next case study. Is not coming out? Wait a second, that I'm gonna test mine. Let's see. Well, eh, if anybody has any problem, please let me know. Uh, I cannot access here exactly, but well, the first question is which are the advantages of a rain grid-based model? Maybe I didn't explain this a lot, but at the end, it's basically that non-static simulation covers the entire area, and I didn't say this. It enables climate change calculations and correlation with present values. Why? Because it's based on precipitation. No? Up to now, we've been well, most of the methodologies are based on flow. Okay, and there is no relation now with climate change predictions. Okay, climate change predictions, as you will see, are related with maximum 24 hours rain or amount of rains in a row, days, rainy days in a row, and things like that. But we don't have a flow prediction. So in this case, it's a good news because we can easily, well, or with a bit of time, we can get the values or how the climate change scenarios would look like, no, compared to the situations nowadays. So that is an advantage of this case. The second question is what information we need with accuracy. Well, this is what I want to highlight here is that what we were talking at the beginning, no, of the keywords of the session, no, importance of having data, but not only any data, no, we need to have the required data for our study and as accurate as possible, no. In this case, all the questions that I put there are actually correct. We need all that, no. We need rain data from several stations. We need high resolution digital elevation models. We need to know the soil nature because we need to define the roughness and the filtration. It it would be essential also to have knowledge about past events in order to be able to validate the models. And well, we need the river network in order to be able to create the mesh. And also, well, if we have real flow data from gauges, it allows not validating but calibrating our model. So in this case, all the questions are true. And the third question is, where do we recommend storing the information? No, I think that is quite clear, cloud server. So well, once this is done, um, I leave the stage to my colleague Marta, that she's going to introduce you the third case study that it's dealing with roads. So Marta, please go ahead and let me see, how can I stop sharing? Stop sharing. I leave you the stage. Stage is yours.
Um, Hi everyone, thanks David. I don't know if you can share the screen for me. Can you share the presentation? Okay, perfect. If you don't mind, David, if you can do you think I can control the screen or can I ask you to go through? Okay. Okay, so the third case that we are going to present today is in the Pacific, is in the Federated States of Micronesia. Can you go to the next slide? This is a country that is located north of Australia, east of Philippines, between Philippines and Marshall Islands. It's a country that is composed of more than 600 islands, in fact, but it has four main islands, one for each island state. In total, it consists of 700 square kilometers, and the primary road network is 360 kilometers long. In terms of inhabitants population, it's a bit over 100,000 population. Here in the right, you can see the four main island states. In the left, top left, we have Yap, which is very close to Palau. Then down Yap, we have Chuuk, and the main island of Bueno, as you can see, is a lagoon that is protected by atoll islands all around and have some center islands in the middle. Then top right, we have Pohnpei, which is the capital, island, the capital state of the Federated States of Micronesia, and down right we have Coast Right. So we are going to do a vulnerability assessment of the road network of these 4 main islands. If we can move. Can we move to the following one? Thanks. So as David was saying at the beginning of the presentation, some of the challenges that he suggested are also faced by the government of the Federated States of Micronesia. The first one is that it is a country that is highly exposed to natural hazards, mainly coastal inundation, because most of the road network lies around the islands in very low areas. So there's quite of a risk of being inundated by storm surges and coastal events, also flooding inundation. Not only natural hazards, but in these countries is also very important the exposure to climate change. As I was saying, as one of the main hazards is coastal inundation. Due to climate change, the sea level is going to rise. So if it's already exposed in the present, imagine in the future. There's a very high impact of climate change in this kind of states. The second challenge is that they have low funding levels. And this is a problem that we encounter in a lot of small island states. So the money that is available every year to do annual road maintenance is not enough to cover all the maintenance needs. So at the end, they create a maintenance backlog. So every year, we are even more behind from the level where we should be in terms of maintenance activities. So the deterioration of the road network is every year a bit higher. The fourth challenge that is particular to this country is remoteness. At the end of the day, as it's kind of far from everything, there's quite a lot of problems in terms of supply of materials, equipment, but even knowledge and techniques. And what does this create? It creates a limited capacity in terms not only of the public sector, but also of private companies. And this poses a problem in terms of managing the road network in an efficient way. And the last challenge that they face is decision making, because they do not have tools to support that decision making in an objective way. At the end of the day, they rely on political criteria or social criteria without the technical view on it. So, having said that, let me show you in the next slide the kind of problems that we face in the road network in Micronesia. Can we move on, David? Here you can see some examples of what we found in the field mission. We have a field mission in August this year, just a few months ago, and we encountered, of course, as I was explaining, the road lies just next to the coast, as you can see in the top left picture. So they are highly exposed to coastal events. In the central picture on the top, you can see some pavement that had been resurfaced like 15 days before we went to the island, and after intense rainfall and flooding of the whole section, it had just been washed out. So that's the kind of things that they encounter. On the right, we can see a slide of an embankment due to the scour of the culvert that you can see there on the toe of the embankment, completely destroyed. And on the center down, we have what was before a 2-element culvert with a pier in between that had completely disappeared because of flooding events. So this is the kind of problems that they face in the country. They face mainly, as we were saying, problems in terms of deterioration of the network, but also of preparedness of the network and the road assets to the hazards that they are exposed to. If we can move, David, please. Okay, so the project objectives. As I was saying, the project name was Vulnerability Assessment and Climate Resilient Road Strategy. This gives us already some tips. What we are trying to set is the base for resilient road asset management. So the first step, the first objective is to improve the knowledge of assets. And how to do that? Collecting inventory data of all the network, pavement, and all the assets, pavements, bridges, culverts, earthworks, you name it, everything. Collecting all the inventory, the typologies, materials, geometry of the assets, so that we really understand what asset we have to manage, but also the condition of the assets. This is very important because at the end of the day, as you are going to see in the following slides, all the methodology for the vulnerability assessment relies on indicators, and one of them is the condition of the asset that is going to impact in the sensitivity of the asset and finally in the vulnerability. So the first objective is to improve the knowledge of assets that we have to manage. The second one is to understand the impact of natural hazards and the exposure to natural hazards in the island. These are also very small islands as Anguilla, but in this case, as we are talking about hazards that are a bit more localized, like flooding or coastal erosion, we can differentiate different segments of the road network that are more exposed or less exposed. This is going to help us study the vulnerability against those hazards. So the second part of the project, the second objective, was to generate hazard maps and really understand the exposure of assets towards those hazards. The third objective is to develop a tool that can help us prioritize. So first thing is to identify vulnerable segments, vulnerable assets, and then do kind of a prioritization of the maintenance needs. And why we are doing that, that's the fourth objective, inform decision making. Provide enough information to the government of the FSM so that they can make decisions in an objective and well-supported way. David? Thanks. So having said that, I'm going to go quickly through the scope of works of the project that they have had a sequential way. So we have started by the understanding of the client needs, the review of the existing bibliography, and also the definition of the existing conditions in the country and project objectives. The second part was the development of the theoretical framework for the project. At the end of the day, as David was saying at the beginning, the framework is kind of common between the different projects, but it has to be customized to each client and each country. So this is what we are doing in the second stage, like understanding the particularities of the country where we are working and adapting the theoretical framework to it. So at the end of the day, we are not inventing new indicators, we are adapting how we calculate each indicator for each country. So for example, the structure of the database is going to be adapted to the kind of infrastructure that you have in that country, the typologies of the assets, the type of assets, the materials. Everything has to be adapted to the reality of the country in each case. The third stage of the project was the analysis of the hazards and the impact of the climate change. So in this stage, we generated hazard maps for flooding, landslides, and coastal inundation for the present scenario, but also for climate change scenarios. After that, we did an analysis of the exposed infrastructure, and this included basically a field survey campaign to collect all data in terms of inventory, but also condition data. With all that data and the framework and the hazard maps, we fed everything into the vulnerability assessment tool that is number 7 that started the development at the beginning of the project, so that we can run the vulnerability assessment, which is number 5, and the risk assessment, number 6. After that, after we have the vulnerability and risk assessment results, we are ready now to do some consultancy work in terms of preparation of investment plans, recommendation on policies and standards of the road sector, and training the government on how to use the tools developed and how to increase resilience of the network. That last three tasks were left at the end of the project once the results from the vulnerability and risk assessment were obtained. David? Okay, as main project outputs, the first one is a road geodatabase. And this sometimes we think is not important. From our point of view, is one of the most important things. And actually, like a lot of countries, they do not have yet data in an organized way, a structured way of their assets, but not only of their assets, of their events like hazard events and failures of the asset. Creating the base of that road database that can be fed in the future with more and more data is crucial, not only for this first analysis that we are running, but even to in the future be able to run, for example, advanced analytics and machine learning. As you may know, like data nowadays is it's everything. Like if we have good and quality data, we can exploit that data in so many things and complete the engineering models and the analytical models that we are developing with a lot of statistical models that can improve those engineering models and provide more information. So establishing a good road geodatabase is crucial for this kind of projects, and it's something that we always tell our clients that they have to really work on that. Even if they do not have a road asset management system or do not do anything else, at least start collecting data because it's going to enable you to do a lot of studies in the future. The second project output, as I was saying, is those hazard maps that we have developed. And those hazard maps are not sector specific. We can use them for this assessment, but they are there for the government to use them for any other thing. They could assess, for example, the vulnerability of their hospitals or public buildings using those hazard maps that we have generated. So they have also a great value in terms of disaster risk management for other sectors of activity. The third project output was the vulnerability assessment tool. Afterwards, I'm going to show you what kind of tool we have generated. It has web GIS functionalities, so it allows you to display all the information and all the data that is collected in the geodatabase. You can display it cartographically in a web GIS, but you can also run different assessments and analysis in terms of vulnerability, risk, or any other indicator of the methodology in a very simple and visually way. The fourth project outputs is the prioritized plan of investments, the program of investments. And this includes two things, like rehabilitation interventions, but also adaptation interventions. We are going to explain this a bit later. The fifth was the proposal of reforms. As I was saying, we had to review after all the other things were completed at first. We had to also review all the policies, the technical standards, and provide recommendations on how to improve those to ensure resilience to climate change and natural hazards in the future. And the last part, last but not least, because it's very important, is capacity building. At the end of the day, if we develop this kind of project somewhere, but we do not transfer the knowledge to the client or the country, and then we leave, we risk that project to be abandoned and not used in the future. So in order to have sustainable solutions that are used in the future and really serve their purpose, we really have to build on capacity in the client. David? Thanks. So as about the methodology and other things were explained earlier, I'm going to focus just very quickly because I'm saying that I only have 9 minutes now. So I'm going to go very quickly on how to use the tool that we have developed to plan interventions. So this is the main screen of the tool. On the right, you have a list of assets, of road assets that you can display in the map. And on the left, you have different indicators that you can use to color assets in one way or another. You can also display at the same time hazard maps. In this case, for example, we are showing Kosrae Island with the, I think it's coastal inundation hazard map and the pavement drone colored by the pavement material. But we could play with different indicators and assets to display anything that we want and have a first view of the island or the state or the country. Right? So we have used this tool to propose interventions at 2 levels or run analysis at 2 levels. We can use it for country level or state level analysis. So in this case, for example, you can see different graphs that we are extracting from queries to the database in terms of vulnerability, exposure, typologies of any asset in the 4 states of the island. So it's giving us a view on which states are more exposed, where do we have more vulnerable assets, which typologies we have mainly in the islands, whatever we want. Any field of the database can be exploited through this part of the tool and can generate the graphs at that high level so that you can make decisions on how to organize, for example, your teams in the government, how to support or how to allocate more money in one state or another, in one region or another. But if we want to go into specific recommendations on what interventions to do on repair or adaptation, we can move to the next slide. And let me show you some cases. So if we want to run asset level assessments, you see here on the left, we have Pohnpei Island. If we select one of the segments of the island, we can access down right an asset sheet where we have all the data displayed and available for analysis. So if we move to the next slide, as we have an indicator-based methodology, we are not going to have only the final risk of an asset. We are going to have all intermediate indicators. So we can run different analysis at different levels, but we can also understand where the risk is coming from. Is it coming from a very high exposure? Is it coming from a high sensitivity? And is that sensitivity due to a very low coping capacity or a very low condition? Those kind of analysis, in-depth analysis of the origin of vulnerability is going to help us propose either rehabilitation or repair interventions if the low vulnerability comes from the condition, or adaptation interventions if the vulnerability comes from a coping capacity. Because at the end of the day, exposure, we cannot change it unless we relocate the road inland some meters away from the coast. Next slide. This is just an example. As you can see on the left, we can see how the overall vulnerability of a road segment, by road segment, we mean a unit that includes all the road assets, like the pavement, any culvert, bridge, earthwork that is included in that segment. They are management units that are useful for the proposal of interventions. So we can analyze in that graph on the left, that vulnerability of the road segment, where is it coming from? And as you can see, it comes from the culvert that they have. There's only one culvert in that segment, but it's very, very vulnerable to both flooding and coastal inundation. Why? Because it has a very low condition, but also a low coping capacity in terms of coastal inundation. So on the right, as we have in the asset sheet, we have all the deteriorations, damages, but also all the design flaws that create that low coping capacity. We can have, with a library of recommendations, interventions that link the damages to the proposed intervention, we have to do a proposal of the specific construction work that you should do in each asset of the network. Next. Okay, so as I have now 4 minutes left, and I think that David wants to conclude the session, this is just very quickly some conclusions, is that the methodology that we are using is scientifically rigorous, is based on international standards, is systematic, transparent, and repeatable. So we have done it with road assets, but it could be done with any other asset of the country. It also enables the understanding of the network and where the vulnerability is coming from. Where are your weaknesses in terms of road management? It also supports investment planning and in the end increases the road network resilience. And some steps forward very quickly. We have to establish data collection procedures to really construct that road geodatabase that I was talking about at the beginning. That's very important. We have to keep calibrating the theoretical models with more data that we are adding. Also, it's good to institutionalize this kind of system so that all stakeholders are involved and get familiar with that. And finally, this can also help the government of the FSN reorganize internally to respond to the demands of the road network in the future. Thanks, everyone. I'm sorry, David, that I only left you 3 minutes to finalize the session. David, we cannot hear you. We cannot hear you. No. It looks like you are on mute. No? No. If you want, do you want me to finish? Like, yeah, if you have the last slides. I think we had also a questionnaire for this last part of the session. I see that there's 11 people watching this. We are not too many, but don't be lazy. Like, scan that QR and try to respond to the questions. We would love to see your responses to that. Okay, do you want to show just the last slide or should we finish here? Want to try it one last time, or if not, I'll go ahead. Okay, I'll go ahead. Okay, so as there's just some concepts that we want to remark, and the first of it is maintenance. Maintenance has a history that has gone from emergency to preventive, now to risk-based maintenance, but at the end is really important. It's not only we cannot only build things, we have to maintain the things that we have in order to really provide that level of service to the users. So maintenance is one of our big words. Data, as I was saying, is really important to run future, more complex models. So this is a call for all administrations to start collecting data, please. Just a very brief example, in Spain now we are running some machine learning models for the railway administration because they have been collecting data for the last 10 years. And that enables us now to run a lot of complex models in order to do predictive maintenance. So that kind of thing is based on data. Please collect your data. Versatility, as we were saying, the same framework can be applied in different scenarios for different purposes and adapted to very different countries. At the end of the day, from Spain to Micronesia to Anguilla, different client needs, same framework, but customized to the needs of each client. These tools, of course, the last objective is to increase resilience, but also do a budget optimization because we always part from limited budgets that are not enough to do the whole maintenance needs. And finally, reduce risks so that we can reduce emergency situations, loss of lives, and impact on the level of service. David, I don't know if you wanted to add anything else, but if not, thank you everyone for staying with us today, and hope to hear you from you. If you have any doubts or any comments, more than welcome. Text us on the chat or email. We will be happy to hear your feedback. Thanks, everyone.